Okay, well, welcome everyone. We have just incredible turnout here today. I want to welcome you all to the Maui Maui Institute for Astronomy's Advanced Technology Research Center. I'm Dr. J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist, and one of the things I get to do is put together these talks and get people like Guy Jette to come and give these fantastic presentations. And I was very fortunate in finding him. He actually found me, and so it suddenly became very easy. The first year I wasn't quite sure who he was, but this is now the third time he's given the talk, so obviously, yeah. And based on the turnout, you guys have all figured out what an outstanding presenter is. So let's see, he has a Master's of Business Administration and also a Master's of Science. He's had a 37-year career with the Air Force. He received the Air Force Outstanding Civilian Center Service Award, the American Institute of Aeronautics and Astronautics, other Economic Technology Committee, or the chair of the Economic Technology Committee for 4 years, the Associate Fellow, the Sustained Service Award. I'm messing this up. I've gone way past my limit of 2 to 3 errors in a talk. But he's also been working with the Kitt Peak observatories for a number of years. He's now retired and is continuing to volunteer time out there doing education and outreach, bringing astronomy to the community, and that's, I'm sure, part of why he is so outstanding as a speaker. And he's part of the Arizona Astronomy Board beginning spring of 2015. So, new appointment that I think that they are very lucky to have him. And we are very lucky to have him here today. Let's give him a nice Maui welcome.
Not this way.
That is how I do it.
Oh, that works out well over the years. Can you ever, how's this, Stefan? Is this better? How's that? Every year it's different. Change. Okay, everybody. No yawning. Hey, no yawning. Okay.
And when you are asked questions, would you please
Repeat.
the question so that people in the remote audience can hear them?
I have a new process for making sure I repeat the questions.
Okay.
I have a new protocol. Okay. So thank you very much, JD. It's great to be back. First question I have is, how many attended my talk 2 years ago on Kitt Peak and the observatories of Southern Arizona? And how many attended last year's talk on globular clusters? How many went to both the last 2 years? That's pretty good. You still came back, huh? 2 years in a row. You know, that's true. And I had a boss a few years ago that he said to me, Jette, he said, you're only as good as your last briefing. So based upon what JD said, I'm kind of concerned. I think I'm putting myself at risk. Maybe I should have quit while I was ahead, but I'm back anyway, so we appreciate that. So tonight what we're going to do is we're going to take a trip through the solar system, and we're going to explore alien seas. I need to define what alien is and what seas are. Okay, alien in this context is basically anything that's not of this Earth. Although we're going to have to look at the Earth kind of as an analog, as a place of departure. But we're going to be looking at other bodies, both planets and moons within the solar system. And we're going to be looking for bodies of liquid, whether they're water or in some cases they're methane. So a body of liquid, be it on the surface or be it subsurface, and also be it currently or be it in the past, or what they think maybe is in the past. And a lot of what you hear, there's a lot of theories out there, and scientists think this, astronomers think that. You know, there's not a lot that's really hard evidence, but there's evidence, but there's not a lot of proven stuff. So a lot of this is theory of where the evidence and where the information is leading us. So that's what we're going to do. Now I talk seas. What are seas? What are seas versus lakes versus oceans? I actually tried to look if there was a demarcation, how you define seas, how you define oceans. And the best I could find is a sea is a body of water that's surrounded by land, which you could say that of an ocean too, of the Atlantic Ocean. But then again, Caspian Sea, the Black Sea, those are more land-bound. But I'm just using this generically to include smaller bodies, which could be lakes, like we have on Titan has a number of, I think there's 33 lakes that they defined, and they've defined 3 seas, or oceans, which are even larger bodies. So it's kind of a loose definition of what an ocean is. Now, the whole concept here is that there is evidence that the solar system has these bodies of liquid throughout, and they've been there in the past, maybe not be there currently, and they think they currently have those bodies. And what we're going to do is I'm going to start with some little bit of chemistry first of all to kind of set the stage, but then we're going to start the exploration on Earth. And what do we know about the Earth in terms of its liquid? Because that's kind of what we know. That's the basis of our knowledge. As we started to explore the solar system, that's what we knew. And then as we start to look at other bodies and how they behave and how they behave in terms of a geologic, not that we can use the word geo, which means Earth, but a dynamic process. And then what happens is we end up knowing ourselves better. So we kind of come full circle. We start with knowing our home planet. As we learn about other bodies and how they act and how they behave, then we end up knowing ourselves better. So that's the kind of the whole concept. So that's where we're going to go. And please feel free to ask questions anytime you want. As we know in the past, we have a lot of questions. This is interesting. It's because it's an operator error, I think. Oh, that's my problem. Thank you very much. JD, let's see, where do we put that? Right here. Hey, thank you very much. That's great. It goes in a USB port. There we go. Magic. Speaking of magic, okay, here's the a body. Looks like the Earth. It probably is the Earth, but I'm going to talk here about where we're going to go. There's this, in terms of why was this body in the solar system, and when we talk about solar system, most of this is going to really apply to extrasolar planets or extrastellar, other stellar systems. We're pretty sure they all have planets. A lot of them have planets around them. And the forces and the laws are pretty much the same as best we understand it. I think the geologists refer to that as Unitarianism, the fact that there's consistent processes throughout the galaxy, perhaps even the universe. So conditions and constraints for a body of liquid, again, whether it's past, present, or whether it's subsurface or whether it's on the surface, there's kind of 3 things. Proximity, proximity of the body to the sun for sure, and even the proximity of the body to a large planet. These can all impact whether there's going to be bodies of water on that planetary or that moon system. So proximity is important. We'll see this in more detail. Gravity. Gravity has several implications. First of all, it helps to have a decent gravitation to hold an atmosphere in the first place. So that's important. And then we're also going to see some of the impacts of gravity that, Jupiter is kind of the big bully of the inner solar system. So we're going to see what the gravitational impact of Jupiter may have had, especially on the inner planets, the terrestrial planets. And then we're also going to talk about tidal effect, which is definitely a gravitational issue. And that's going to play big, especially when we get to the outer planets. And then the last thing is force field. We'll see what that is, a force field that protects planets and also can protect moons as well as planets. So those are the 3 places we're going. You'll see more about these later. First thing I want to point out, this is a subset of the periodic table. It goes to atomic number 30. And this is a logarithmic scale, so each of these hash marks, 10, 10 to the second, third, fourth, each of these is 10 times the previous. What this shows you is hydrogen, regardless of the absolute number, but its abundance is basically 10 times that of helium. And then the next most common, if I'm reading this correctly, looks like oxygen, which is quite a few times less abundant, but still, oxygen is the second most common element in the solar system. And for that matter, we don't have any good information that says that other systems are much different than the solar system. Okay. So oxygen is a biggie. And then if you go across, carbon is up there pretty high. And then neon, we don't worry about neon, just like helium, that's an inert gas. Well, there's neon on Earth and the sun, or I mean on Earth. Magnesium, silicon, iron, these all make up with oxygen the Earth we stand on. You have silicon dioxide, these 2 very abundant elements. You have magnesium sulfate, magnesium, sulfur, and oxygen, and then iron oxide. So this first tier, these are very common not in an absolute sense, but in a relative sense, because again, the big hitter here is hydrogen and helium. Now, so what's important, everyone knows oxygen and helium, number 1 and 3. And we all know that that forms a very common, if I can find it, a very common compound, right? 1 atom of oxygen, 2 atoms of hydrogen. We know what that is? That's water. So if that kind of indicates that there's a potential for water being very, very abundant, not necessarily in the sun, because most of this is in the sun, not counting a lot of it in Jupiter and Saturn. But that just kind of bodes well for the fact that the water is not an uncommon compound in the universe. The other ones, I should say, you get 1 atom of carbon and 4 of hydrogen. What is that? Pardon? Methane. Again, they're common. We got carbon and hydrogen. This is maybe number 2 or 3, and hydrogen. Yes? It wouldn't quite be this high, but Jupiter is pretty big. And Jupiter is made of hydrogen and helium, as is Saturn. And then Neptune and Uranus, they're made of hydrogen, helium, and also some methane. That's a good question, though. It'll be, I would say, if you saw the same thing on the level of the non-solar part of the solar system, these would drop down perhaps 1 or 2 orders of magnitude. Pardon? 2, yeah, okay. So 2 would be right here. And I didn't want to go down too far, but I'm happy they go down further because you still have quite a bit of helium and hydrogen out there. Okay. So the other thing that is interesting is if you get just going to show you if I have 1 atom of nitrogen, it's not on the first tier of the most common here, but it's pretty high up. It's on the second tier, just like nitrogen, sodium, which we'll see later, aluminum, a lot of aluminum in the Earth's crust, and calcium. But nitrogen, where am I? I'm back to nitrogen and helium. NH3 is what element? Ammonia. You guys are good. Yeah, that's very good. Now, the next one may not be quite as easy. Another one of the hydrocarbons, if I take 2 atoms, I wish you could see this back there, 2 atoms of carbon and 6 of hydrogen, so it's C2H6. What is that element? That's close. Acetylene, I think, is C2H2. Pardon? Ethane. Are you a chemist? That's right. It's ethane. That's very good. Okay, it's going to get more complicated. This is the last one, I promise you. This is also, by the way, this is the dog molecule. Doesn't it look like Rover? It is 3 atoms of carbon and 8 atoms of hydrogen. Anyone know what that one is? I should have kept a door prize for this one. Pardon? You're right. How'd you know that? Whoa, that's propane. Okay, so anyway, it just shows you these are common elements, water for sure, methane, ammonia in the outer solar system for sure, even propane, ethane, acetylene, someone said, C2H2. So they're very common in the solar system. And you can see, based upon this, these are not uncommon elements. Okay, that's enough for that one. I just wanted to give you that background on the elemental abundance. You come just for the graphics, don't you, right? Okay. Do you suppose there's life under other rocks? Or do you suppose there's life on other planets? Yeah. Should have followed me. I hear life under some of those rocks. Okay. Now, there's 5 lines of reasoning why scientists think that biology may be common in the universe. The first thing is, as we just saw, the ingredients of life, and we did talk about silica and oxygen and some of the rock items, but if you remember last year I talked about globular clusters, and I talked about what the elements that were common to life, and there was hydrogen, there was nitrogen, oxygen, carbon. Well, those are all in that same top 2 tiers we just saw. So the abundance of the elements required for life are quite common. In addition to those being common, those elements being common, the formation of those molecules is considered to be a relatively simple process. They form relatively easy. Now, how you get from organic molecules to life is a big leap, but the actual organic molecules form easily. And not only do they form easily, but once they form, they basically can survive a wide range of conditions, and life does too. I mean, life we'll see, can survive extreme conditions. They call that type of life extremophiles. And habitats, there's lots of habitats that we're seeing more and more. One time we thought, well, there might be life on Mars or Venus, but forget about those far planets at the end of the solar system. There's nothing there. Well, they think now there's possibilities. There could be things there. So lots of locations. And then life's been around a few billion years, probably pretty basic life, but stromatolites have been around, I think, 3 billion years. So life seems to be long-lived, so to speak. So these are the reasons why they think that biology may be common, and in fact, may be not only common, but very common. How many think that there's no life at all, other life in the universe? How many think there's life in the universe? How many think there's sentient life? No, not everybody thinks there's sentient life. Okay, that's interesting. So now that brings up the question, how NASA defines life. NASA defines life with 6 words. Chemical systems capable of Darwinian evolution. That's how NASA defines life. Because I know you've all probably read articles, different ways you define life and what's life, but that's life as we know it. That's how NASA defines life. If you saw the Neil deGrasse Tyson, Cosmos, this was one of his guest stars. Anyone remember what the name of this little bugger is? That's close. Pardon? Tardigrade, that's right, tardigrade. This little guy here, he is really kind of cute, isn't he? He's the size of a poppy seed. So I know, Cindy, do you ever treat any animals this small? We have a vet. Pardon? Fleas? Okay. You probably get rid of bugs this small that are on your animals, right? Pardon? Treats them harshly. So, tardigrade, okay? And he is pretty significant because he can survive boiling water, freezing temperatures. They've sent these guys into space. They can survive heavy radiation. They can survive cosmic rays, the vacuum of space for extended periods of time. So that's an example of a life form adapting to a very extreme condition. That's why they call them extremophiles. Now, we don't have to find life in the universe to find out that there is life in the universe. All we'd have to find out, or all we have to find, is evidence that there was life. This thing here, is this alien life? Is this some or somebody's depiction of alien life? Anybody recognize that? You don't recognize that? Okay. Well, hallucigenia, this is his or her name. And this is a 500 million year old fossil. Everyone's heard of the Burgess Shale. Do we have any Canadians in the room? No Canadians? Because Canadians might recognize this. They come from British Columbia and the Yoho National Park. They found in the early 1900s the number of soft-bodied, very early life that would survive the deposition and fossilization process. And this was one of them. That is pretty bizarre. But it is, in fact, something we might, if we found a fossil like that on Mars, on some other system, that would kind of tell us there has been life. And then lastly, we don't even have to find fossils. We could find some 100,000-year-old life form that used to exist that was drawing photo, like the petroglyphs we have in caves in France. And we might find something like this someday. If it feels good, it feels good knowing that long after we're extinct, we're still remembered for artistic skills. No one knew that the mammoths drew their own photographs. And that's kind of some music to kind of go with that mood, the prehistoric mood, the prehistoric hunter. And by the way, I got more music coming up, so feel free to name the tune if you recognize. Those are kind of obscure, but the other ones may be easier if you'd recognize. Okay, I want to start, before we go to the Earth, put things in perspective. Now, most of you, I know a lot of very serious amateur astronomers, but I want to just point out a couple things here. In the solar system, and this is not accurate by distance, okay, because the sun is about 870,000 miles in diameter. So if it was the size of a foot, not a basketball, is roughly 12 inches in diameter. If it was that size, then the Earth's going to be at 93 million miles, 100 feet away almost. And Pluto's going to be a mile away at 4 billion. Of course, it has a very elliptical orbit, so it varies quite a bit, but roughly 4 billion, about a mile away if this is the size of the sun. So that's not accurate this way, but the sizes are relatively accurate. And what you notice here is something kind of interesting. There's 5 areas, 5 zones, if you will, in the solar system. There's the terrestrial planets that we're all familiar with. Of course, the Earth is the third one. And then there's a asteroid belt between Mars and Jupiter. And Mars sits out there at about 150 million miles, 1.5 astronomical units, an astronomical unit being distance between the Earth and Sun. And Jupiter is about 500. So these are your gas giants, and then recently they started calling Uranus and Neptune the ice giants. And then you have Pluto out here in the Kuiper zone, the Kuiper belts, and then much, much further out you have the Oort cloud. So those are the 5 areas of the solar system. But we notice here, when we talk about where bodies of liquid would be, proximity has an impact, because you're not going to expect bodies of liquid on Mercury, although they have found ice in craters, and then they think there could be some subterranean ice on Mercury, but it's not conducive because it's so close to the sun. And of course we have bodies of liquid on the Earth. Venus, we think there was water at one time as Mars. So proximity is important. Even proximity of some of the moons to these large planets, because of a reason we'll talk about later. So proximity, these 3 factors kind of work together. There are conditions, but they are also constraints. And the other constraint is gravity. It's nice to have a decent gravity to hold on to the atmosphere, for one thing, although that's not everything, because if there's some other conditions which we'll talk about that would preclude even a decent gravitational body from having an atmosphere. And you really require an atmosphere for you're not going to have liquid on the surface of a body unless you have an atmosphere. And we know why that is? Pressure. There's no pressure. Just like if you take water right now and you take it up to Haleakala, it requires a lower temperature to boil. It doesn't boil at 212 degrees Fahrenheit or 100 centigrade. And the higher you go, the lower the temperature is. Eventually you go to space, it boils off at very low temperatures instantaneously. So without that pressure of the atmosphere, you don't get to maintain a body of liquid. Some crashing. Okay, this is interesting. So this ties into what we just looked at, proximity, because this is a condensation chart, condensation of solids. So we have, again, astronomical units. The Earth is here at 1 astronomical unit, and here's the temperatures you can see here. And as we go out, we go to where Jupiter is at 5 astronomical units all the way out to Uranus. And what happens is close in, we have the metals basically condensing from gaseous to liquid to solid. And the further out you go, you drop down. Here, silicates and rocky material form. Water ice becomes solidified out around the asteroid belt and around Jupiter. And ammonia ice further out around Saturn. So this condensation of solids kind of follows the proximity you are to your star, in this case the sun, kind of drives what type of materials are going to condense out on your body, your moon in this case, or planet. Now, I call this planet ocean because I don't know why they call it planet Earth, because it's 71% of the Earth is covered with water. 71%. And to an average depth of 12,400 feet. So 2.5 miles is the average depth of the water. So we ought to, in this picture here, you almost have an entire hemisphere that is a water hemisphere. So 71% is water, so we ought to call it planet ocean. In addition, 97% of the water on the Earth is basically tied up in the oceans. And the water is extremely important, they think. They're not sure of some of this, but they think the water is important for plate tectonics, because the water is required to lubricate these plates that move, the subduction zones, and without water, you don't get this dynamic active Earth with these plate tectonics. So that's an issue. And what drives the plate tectonics, in addition to having water, is you have to have basically a core which is hot. Because we know there's a lot of heat in the Earth, because look at the volcanoes. Look where we're sitting on the results of the hot interior of the Earth. Where did the water come from? That's a very good question. So 2 things. The theories go back and forth. For the longest time, it was I call it the proplanetary disk. I've never seen a good name for this theory, but basically what that says is when the solar system formed, you had all this material that was in this big cloud, and it slowly started revolving. The gravitation took over and it's formed into the sun, formed into the planets. And this theory says that all these elements that we saw earlier were kind of, spread equally throughout this planetary disk. It's just a big disk, and there's nothing that initially that had any greater gravity or concentration than any other part of the disk. So it was all there in the first place. So the theories are that when the Earth formed, it already had the water internally, and then through the expulsion of volcanoes, a lot of that water came to the surface. Same thing would have been true for the other planets. They'd have the same issue with water. Water would be common in its formation. But then they started talking about, well, we think they came from comets. That the comets, bombarded the Earth, and we got a lot of water from the comets. Although recently they did a study, there was some comet they studied, and they were concerned because they weren't concerned, but it was a little bit of evidence against the cometary theory because they had the wrong form of deuterium. Deuterium is an isotope of hydrogen, and it wasn't the right concentration of deuterium. So they thought, well, the Earth's oceans couldn't have formed from that kind of a comet. Maybe there's other kinds of comets. And then in the last recent few years, they think that what they call is late heavy bombardment. The Earth formed about 4.5 billion years ago, and they think that about 4 billion years ago, about 5 to 600 million years after the formation of the Earth, there was what's called the late heavy bombardment. And the late heavy bombardment was where, and I think I can show you on this next chart, if I remember the right chart that's up here. Okay, back to this chart, because we used to think that all the planets formed kind of where they are. The Earth formed right where it is, Jupiter formed right where it is, etc. Well, now the theory in the last 10, 15 years is that this is not true, that Jupiter moved in. Jupiter was further out, moved in. Neptune was further in, moved the other direction. So what they think happened is you had a lot of debris, more so than what they have right now, plus the asteroid belt. It was a belt of material that either Jupiter destroyed a planet that may have been there because of the gravitational pull, or it prevented the formation of a planet where the asteroid belt is. But they feel that Jupiter basically moved in, gravitational effect of that, it kind of slingshot effect, threw a lot of this material into the inner solar system with this late heavy bombardment for a couple 100 million years, and that's where a lot of the water came from. That's one of the theories that is more popular now in terms of heavy bombardment. Now, there's not much evidence on Earth because we resurface the Earth periodically through volcanoes, plate tectonics. Venus resurfaces frequently through a lot of volcanic activity on Venus, which I think they say that there's 4 to 5 more times volcanic activity has been on Venus than on Earth. Mercury's got a lot of craters, and the moon, they've actually taken some of these rocks and they've aged them. And the highlands, when you look at the moon, you got the mare, the Latin for oceans or seas. It's really basalt that formed these big flat lava beds. But the highlands are bright colored, and they've dated a lot of the craters in the highlands, and they fall right into this time period. That's why they think it was hit by this late heavy bombardment. And I think the next chart I show the asteroid belt here. Here's the belt between Jupiter and the inner planets, and Jupiter moved in, took a lot of this stuff and basically threw it in, and we got bombarded for a few 100 million years. So that's one theory, and probably the answer lies somewhere in between. It's probably a combination of a lot of water was there was always been comets coming in, asteroids, and then late heavy bombardment added to that whole issue. Yes? Right. I think that was the comet CG it visited. I believe that was the name of the comet. Rosetta visited, and they found that. Yeah, that's okay. It's interesting. The question is, when they measure deuterium in the oceans, they probably just take a few samples. And how representative is that of the average deuterium in the ocean? So I'm not too sure, but I would think that that'd be a great science project for some college student, an oceanographer type college student, to go and to take multiple samples of the water to check what the consistency of the deuterium ratio is in hydrogen. Maybe they've done that. I'm not too sure if they've only measured a few places or they've done extensive. But you're right. You would think there could be variations. Just like one comet doesn't necessarily mean that water didn't come from comets. You'd have to look at a lot of comets. Yeah, but it's interesting. Don't know whether the oceanography community has ever extensively studied that ratio, and deeper especially, harder to get down 4 or 5, 6 miles. Yes. Right. Well, it's 8.5. Let me go back. If I can go back. How far back was it? Just one slide back. Not beyond that. Forward. You just want to hear the music again. Oh, it was, okay, I know which one. It's the one with the condensation. Is that the one? Well, if this doesn't work, I can find it more quickly. Right here? Yeah, because it's 8.5 or 8 1/3 minutes. Wasn't that one? Oh, I know. It was a scale down here. Okay. Okay, so here's the Earth right here, and light minutes. But this should go down. I mean, 8.5 minutes would be right about here. It's not too far off. It's yeah. Okay. Okay. But you're right. 8.5 light minutes. Just like it's in the other direction, way out at Pluto. It's like 5 light hours out to Pluto. Oh, okay. We don't want. Oops, we went too far. Okay. Now we talk about all that water on the Earth, where it all come from, and it looks like there's a lot of water. But when you think about the Earth, it's about almost 8,000 miles in diameter. Okay, and the ocean is only 2.5 miles average thickness. So it's almost like if you had an egg, it's like one drop of water on an egg. So in an absolute sense, this is all the water on the surface of the Earth. That's not much. It looks like a lot more than that. When you look at that, that is a sphere 860 miles in diameter. That's all the water, fresh and salt, okay? And if you then take out of that 860-mile diameter sphere all the fresh water, you get a sphere 170 miles in diameter. And that includes all the freshwater lakes, rivers, and also all the frozen water in Antarctica, the Arctic, Greenland. And then if you take out of that big sphere all the readily available water, i.e. you don't consider the frozen water on the Earth, we only have freshwater lakes and rivers, a sphere 35 miles in diameter. So that's not a lot of water when you think of it. Now, don't feel too bad, because they are thinking that there's just as much water below the surface, underground, basically. I mean, that's little ways underground, quite far underground. There may be as much water beneath the surface as on top of the surface. But, I mean, when I first saw this, I was kind of surprised, because I would have thought there was a lot more than that, based on what you see. But it's such a thin veneer. So, a coat of paint, absolutely. It's like we're astronomers, right? Amateur astronomers. Some of you are really amateur astronomers. I'm a theoretical amateur astronomer, and I'll explain what that is later. It's not a real amateur astronomer. But if you talk to the astronomy community, I just lost my train of thought. Where are we going with that? Okay, well, it'll come back to it later. Okay, now we have a magnetic field. The Earth has a magnetic field. And scientists aren't exactly sure exactly how it works, but they have an idea. And the idea they have is that you have a solid inner core made of iron, and you have an outer liquid core, also iron, and that is liquid, and that's in motion. This is Coriolis effect. That liquid is in motion. So what you end up having is 3 conditions for this dynamo, this geodynamo, which creates the magnetic field. You have an electrical conductive core, because it's iron, and you have convective currents. This liquid is moving, and then what causes this to some degree to move is the rotation of the Earth. It revolves once every 24 hours. So with these 3 conditions, that dynamo basically creates the magnetic field. As best they understand it right now, how the magnetic field of the Earth works. Pardon? Pardon? Okay, yeah, it's a dynamo. It's a unipolar dynamo. You remember the old magnets in school? You have a magnet, and you put some filings around it, and you got these, the magnetic field, okay? Now, what that creates is, with the solar wind, because we got a lot of charged particles coming from the sun, and when those charged particles come to the sun, those charged particles, in conjunction with this magnet here, the Earth, you create a magnetosphere. And the stronger your magnetic field, the stronger your solar wind, the stronger this magnetosphere is. And this magnetosphere is important because it prevents a lot of this radiation, a lot of the harmful UV radiation, charged particles from hitting the surface of the Earth, except highly charged particles, like when we have a solar storm or coronal mass ejection. They can't get through to the equator area, but some of them get through the lines of magnetic field lines up to the north and south, go into the northern pole, southern pole, and we know what that creates. That basically, the upside of that, it may knock out satellites, but it gives us some great aurora borealis in the north, aurora australis in the south. And you know, I can't give a talk here without showing aurora, right? I managed to figure it in one way or another every time. So, I mean, look at that. It's incredible. Anybody ever seen, has anyone ever seen aurora like this? Okay. A few of us, that's good. I have not. I saw a rosy red sky once from Albuquerque, New Mexico with a coronal mass ejection, but all it was a rosy red sky. Yeah, oh yeah, yeah. Oh, the rosy red? Yeah. And of course, if you're around in 1859, what's called the Carrington event, there's a very large magnetic storm that you can see the aurora in Hawaii. Anybody here in 1859? Probably not. Hey, he put his hand up. I'm worried about him. So, one interesting little tidbit about this is cool. This is that aurora ring around the pole. They just found out recently that there was a connection between aurora and lightning. That if there's an increase in solar particles, like in a coronal mass ejection or a big flare, it actually increases the number, and I'll shut that music off, it increases the number of lightning strikes. Yeah, and it makes sense because you got all these charged particles in the atmosphere, and lightning is just charged particles, but I've never seen that, I've never heard or read that connection before, and now they're saying they've actually got proof this actually happens. So now we're going to talk, we talked about this magnetosphere. Basically, that's the force field. That's an important consideration in whether you have and can retain a liquid body on your surface is a magnetosphere. We'll talk more about it a little bit. But the other thing is important in this whole realm of what causes liquid to form and to be maintained are called the tidal effect. And all that is gravity. And you have the sun here, of course. We're all familiar with tides here in Hawaii. When the moon and the sun get together, you have an extra high tide. And the thing that I wasn't aware of until I was putting this together, the relative tidal effect of the moon versus sun, because they both help create tides. And the sun's a heck of a lot bigger than the moon with mass, but it's a lot further away. So what do you think has the bigger influence, by what degree, the moon or the sun? By how much? Close. That's really good. Twice. Well, let me put it this way. More than twice, which could approach 3. But it's more than twice the effect of the sun. That because of the moon being close. And again, the whole tidal effect, we'll talk more about this later. It's not so much the gravity. What it is, it's the gradient. In other words, even in this case here, we'll take this one down here. When you have this gravity pulling this side it pulls this side of the Earth and the oceans more than this side. Although to some degree, it pulls the Earth in this way. So some of this tidal effect is because the Earth is pulled this way as well as the tide and Earth this way. So it's a gradient. Now, the next chart. Oh, by the way, that's a powerful. I mean, gravity's powerful, but the tidal effect. These are the mice. You've seen these, 290 million light years away, and these are tidal tails, also called galaxy tides or galactic tides. And what the idea is here is these two have passed each other, and when they pass each other close, they grab material from each other and they stretch this tidal tail out. So there's a number of these if you look at galaxy photographs. So it stretches to the far reaches of the galaxy or the galaxy realm. NGC 4676. Now, this is basically the inverse square law. This law applies to gravity. It applies to sound. It applies to light. And the concept here is if you're twice the gravity basically acts like it's at the center of, in this case, we'll call it the Earth. So you have a certain gravitational effect on the surface. If you go twice as far from that gravitational center, it's 1/4 the gravitational force. If you go 3 times farther, it's the inverse square law. 1 over the inverted 3 squared gives you 1/9. If you're 5 times the distance, inverse the 5, 1 over 5 squared, 1 over 25, 1/25 the strength of gravity at that distance. So that that drop is significant in terms of it doesn't take long to get way out here and not have much effective gravity. Okay, now we're going to everybody recognize this body? Venus? Why wouldn't you say that? Oh, it's what's his name? Frankie Avalon saying Venus. Well, that's interesting. Oh well. Maybe we'll turn. I can't turn the volume down. Okay, I guess Stefano is controlling the volume. So I call planet mysterious because for the longest time we didn't know what was under those clouds, those thick clouds. And this is a UV picture right here. That's ultraviolet. But we had no idea. And in the 50s, what it did, it basically, you had Frankie Avalon singing about Venus, and you had we've had a number of flights. We've had Mariner in '62, and we had most recently the Venus Express, which was the European Space Agency, and we had Magellan. Magellan was a radar imager in the early 2000s that took some great photographs finally beneath that. But before we got beneath there, we had Isaac Asimov writing about the lucky star and the oceans of Venus. We thought there was oceans in Venus. And there's even this song, I won't go through it, but the Ventures, they had a song called The Love Goddess of Venus. There was even a movie with Zsa Zsa Gabor that was the queen of the universe, about this Venus having this planet of women, and these guys landed in a spaceship, and they were outlaws because they killed all the men because they didn't like the guys. So there was a lot of stuff going on in the 50s about Venus, and a lot of thoughts about what was beneath. Pardon? You wanted that one, huh? You Google it, right? So this is what Venus looks like underneath all that heavy carbon dioxide. Basically, is what the atmosphere is. This is the radar image, of course, with the Magellan. And the question is, what's strange about Venus? Pardon? It's dry. Well, there's a lot of things strange about Venus, but a couple of them that come to mind is, all of us, the Earth, if the sun is right here in my hand, we all go around the sun from the top counterclockwise, and we rotate on our axis counterclockwise. Well, Venus, it goes around the sun counterclockwise, but it doesn't rotate counterclockwise. It goes around the sun the same way we're going, but it rotates in the opposite direction. Ah, very strange. Very, very strange. And one reason it does that, they think it was hit, maybe late heavy bombardment, hit by a very big body that reversed its rotation and slowed it down considerably, because the other strange thing about Venus is the day is longer than the year. A day on Venus, it takes 243 Earth days for Venus to rotate on its axis once. And it only takes 224 Earth days for Venus to go around the sun. So its day becomes longer than its year. That's a very strange thing. That's that very slow rotation. And why do we think there was abundant water one time on Venus? We kind of alluded to it earlier. Well, there are some indications, lake beds. Yes, there are lake beds, and it looks like rivers flowed at one time on Venus. But I think the biggest, most compelling thing is this late heavy bombardment, the fact that we all formed out of the same protoplanetary disk with the same material. So the idea is if there was water on the Earth, and it still is, there was one time water on Venus, water on Mars, and Mercury. That's a big indication they think there was water one time on Venus. And here's one of those radar images from Viking also of Venus. So where did the water go and why did it go? Well, it is pretty hot, but that's a good point too, because right now the surface of Venus is like 900 degrees Fahrenheit because it's greenhouse effect gone crazy. And the pressure on Venus is 90 times what it is on Earth. So that doesn't bode well. That's why it's so hot there. But at one time they thought that there was plentiful water, like oceans of water, on Venus. And what they think happened is Venus, if it wasn't for the fact that it was a greenhouse effect, I have read, although I can't verify this, it seems like it's not accurate, but I have read that Venus would only, if you put the Earth where Venus is, because of the proximity to the sun, it only would be 20 to 30 degrees warmer. which seems it would be more than that, but that's what they say. 20 to 30 degrees warmer, not hundreds and hundreds of degrees warmer. So a long hot day. Yeah, in the wrong direction. Because retrograde means on Venus, sun rises in the west and sets in the east. So it's a complete reversal from Earth. See, now, where the water went, they think. We talked about that dynamo of the Earth, that geodynamo. And what keeps the Earth's dynamo going? Well, one, we have a nice hot core. Well, Venus isn't much smaller than the Earth, so it has that same kind of, we think theoretically, that same iron metal core, that the same core as we did, and it's the same size, so it isn't like it's a small body that cooled off. It's pretty hot, so it should have a dynamo. It's got the iron, most likely, and it's got that dynamo going. It should have been hot enough. However, what they speculate, pardon? No magnetosphere. The reason, and at one time they think it did have no at one time it had a magnetosphere. Why no magnetosphere? Because the rotation is extremely slow, and according to theories, you can't have a magnetic field and therefore a decent magnetosphere unless you have that rotation. So as soon as that alleged large body hit Venus and stopped its normal rotation, slowed it down, and went to the direction, that got rid of the magnetosphere, and when it got rid of the magnetosphere, you're so close to the sun, all that ultraviolet radiation came in. It took the water, and through dissociation, it broke out the water molecules. Hydrogen dissipated up into the sky. Oxygen, they think, formed with carbon dioxide, creating all that carbon dioxide. Now you still have these thick clouds, even without a magnetosphere, but you have volcanoes that are maybe 5 times the volcanic activity of the Earth has and it has had in the past. So it's likely that because of that volcanic activity, that's one reason why Venus is maintaining an atmosphere now, but a greenhouse effect, runaway greenhouse effect atmosphere. Yeah, yes. Yes. It's the only planet, yes. The question is, yes, the question is it different than the other planets? And the idea is yes. Now you get out to Pluto and Neptune, they kind of have some strange rotations, but they're not counter complete like Venus is. Because it's relatively straight up and down like we are. It's not like its axis on its side, like some of the outer planets are kind of an oddball axis. So it looks like, and it's strange because when that primitive protoplasm or that protoplanetary disk got going, it was all going counterclockwise, and you were spinning counterclockwise. So the fact that it probably would have been, they don't think it, from a physics point of view, it could have gone counterclockwise with a revolution, and then clockwise with a rotation. That doesn't make sense. It kind of rotates in the same direction that it revolves. Okay. So this, this is a picture of. I'll give you A, B, C. Is this A, the Vog from the Big Island? Is it B, the Maui cane burn that we all enjoy in the Christmas holiday special, the Maui cane burn? Or is it Venus? It's Venus, and it is sulfur dioxide. So all this sulfur dioxide, rotten egg gas, right? All this is being put in a million times more sulfur dioxide in the atmosphere of Venus than on Earth. Any question? So this could be part of that greenhouse effect, the combination of carbon dioxide and sulfur dioxide. Okay, this is interesting because we talked about the Earth and Venus. Here's Mars. Here's Mercury. Interesting. 2 moons, Jupiter's Ganymede and Saturn's Titan, are bigger than Mercury. 7 moons are bigger than Pluto. Not that Pluto's a planet anymore, but some people still are upset about that. Anybody still upset about Pluto not being a... Look at that. We got 3 or 4 people still upset about Pluto not being a... Yeah, okay. Oh, even Ned, right? Okay, yeah. Well, I got a T-shirt for you. A T-shirt that says, it kind of shows your age. It says, in my day, we had 9 planets. But you kind of date yourself if you wear that T-shirt, right? Okay, bonus question. Here's the bonus question. How many, and this is 2 months old. It could have changed. The data was back in November. How many natural satellites, moons, do we know of in the solar system? How many are there? Well, a lot. Okay, you get extra credit for that. Give you 2 points. Hey, 5. 5 they know about Pluto. Anybody have any thoughts? 140? That's pretty good. 120. Well, you know, I'll give you a hint. Jupiter's got 67. So it's got to be more than that, right? And Earth's got one, got to be 68. Now, the answer is 173. Because you have over 60 around Saturn, you got 14 around Neptune, 5 around Pluto, 2 around Mars, us, and did I miss Saturn's got almost 60. So 173. The significance of that is not just a trivia question, because you think we got 8, or for some of you, 9 planets. But what this means is there's 20 times more moons than we have planets. And the thought now is that when you're looking for life in the solar system or elsewhere, you can look at planets, but you're not going to have much luck if you look for life as we know it on Jupiter or Saturn. But the possibility is some of the moons around these planets. Not only when you look at the solar system, but other stellar systems are going to have gas giants like we have. They probably aren't suitable for life as we know it, but they may have some really cool moons. Just maybe like Earth-like moons going around these large gas giants. So that's the significance of that 173 number. This is a false color image, but this picture is actually from your mom. Your mom was a spaceship launched by the Indian Space Research Association called Mars Orbital Mission. So that's your mom, okay? What's unusual about Mars? And it's really not that unusual. We know about this. Well, the big unusual thing is there's a substantial and widespread evidence of past and present water flowing on the surface. I mean, really, really significant. And you recognize that. What was the music? That's good. He's getting lots of points tonight. Are you keeping track of the number of points? Oh, okay. Oh, okay. Did you notice with Venus we also had the host suite for Venus? Maybe it wasn't on there very long, but that's really good. And that's significant because he hosted 7 movements in that suite. Okay, the planets, and he wrote that between 1914, 1916. So this is like the 100th anniversary of Holst, the planets. Yeah. He didn't do one for Pluto though, even though he lived 4 more years after Pluto was discovered. But I understand that he was so upset. Imagine being upset by this. He was so upset that the planets were so popular, they took attention away from his other works. So he kind of just said, I'm not going to do Pluto. I'm just upset about that. Yes, question? Yes, they do. Yes, they do. Do any of the moons have magnetospheres? And the one that there's 2 kinds of magnetic fields or magnetospheres. What they found on Ganymede, the largest moon, I think it's the largest one in the solar system, largest one in Jupiter, they found it has an intrinsic magnetic field. So it's got the what they think is liquid, that liquid iron core, it rotates, and there's a definite magnetic field. And then what happens is it has that magnetosphere that's created more so by the strong magnetic field of Jupiter than it is by the sun. So that magnetosphere is caused by Jupiter more so than the sun, and you're right. Yeah, so I'm pretty sure that's the only planet that has its own magnetosphere. Now, there's a couple others we'll talk about later that have intrinsic magnetic fields, and we'll talk about those, I think, coming up pretty quickly. Okay, and Mars, talking about Mars. We all know this gentleman, Percival Lowell, back in the late 1800s, Lowell Observatory in Flagstaff, Arizona. He was a rich Bostonian, went there, built a nice observatory, 7,000 feet. Still has an observatory there. They just put a 4-meter knot in downtown Flagstaff, about 20 miles out in the dark sky area. So he, in the late 1800s and early 1900s, as you all know, he looked at Mars. He saw canals. He thought he saw canals, and he speculated these canals were built by sentient beings to bring water from the ice caps, because there's ice caps on Mars that have carbon dioxide for sure, but also have water, and bringing this water down to a dying civilization. So that kind of caught on in the U.S., and there was a big craze, and the catalyst was things like War of the Worlds by H.G. Wells, late 1800s, and then Princess of Mars. Who hasn't read Princess of Mars by Edgar Rice Burroughs of fame, of Tarzan fame? Most people recognize him as Tarzan more than Princess of Mars, but he wrote a number of novels on Mars. So this was a big thing. It started this whole genre of science fiction and Martians and all that. And then, a couple years ago, he wrote Princess of Mars in 1912. And then in 2012, There are winds on Mars. You probably can't hear them, but it's not that much atmosphere. So this is Mars. Anybody recognize this? Pardon? You got it. You got it. John Carter. Yeah, in 1912 they did a movie called John Carter Mars. Anyone see that movie? It was. I thought it was a pretty good movie. It didn't do very well in the box office. My theory is they didn't call it Princess of Mars. Wouldn't everybody go see the Princess of Mars? They called it John Carter Mars. If you don't know about it, who wants to go see John Carter Mars? It was a good movie, and it was on the 100th anniversary of Edgar Rice Burroughs when he first published Princess of Mars. So anyway, Mars has been a big part of our consciousness in terms of Martians and science fiction in the 50s and 60s. This is another picture from your mom, the Indian Space Agency, the Mars orbital mission. And the cool thing about this picture is, I've never seen a picture like this of Mars. On the limb, you can see this thin atmosphere on Mars. And Mars's atmosphere is like 1/100th the atmosphere right here on Earth. Okay? It's like being up at 100,000 feet. In contrast, Venus's atmosphere is almost the reverse. It's 890, figure rounded to 100. It's 100 times thicker than the Earth's atmosphere and the pressure on the surface of the Earth. This is 1/100th. So it's kind of there's a balance there. And here, if you look at this picture of Mars, I'm pretty sure this one was taken, as most of them are, by the HiRISE. The HiRISE is the high-resolution imaging system. This is on a Mars orbiting satellite. It's been there for a number of years, taking great high-resolution pictures. So this obviously looks like a riverbed, although it could be a lava. It could be an old lava bed, too. They're not quite sure. But they think that, hey, I kind of would go with the water on this one. Pardon? It could be CO2, but that's a good point, because they think there's like 100,000 different rivulets and things they've seen, and they've seen these active changes in these rivulets that were there that weren't there last week that are there this week, and they think a couple things could happen. Not only could it be water temporarily, although the low pressure is not going to stay long, they think it could be liquid carbon dioxide, which is coming up from below the surface and causing these terrain features. So they're not too sure, because there's a lot of carbon dioxide atmosphere on Mars, very thin, but it's carbon dioxide, just like Venus. And then if you look at other, that right here, one thing you want to do is you want to look, this is not necessarily that convincing, but if you want to look for beachfront property, we can be familiar with that here in Maui, right? The beachfront property. You want to look for what's called the benches or the terraces that are created by lakes and bodies of water. And if you find that, maybe you'll find the water. So if you look at some other photographs of Mars, HiRISE, you got some interesting things here. Boy, that sure looks like a river channel. But then again, it could be a volcanic flow, but it kind of looks like water. And here's some of those rivulets coming off this ridge here that will darken, and look at it a week later, and there'll be some longer ones here, and then it'll dissipate. So is it carbon dioxide? Is it water? What exactly is it? This looks like a bench to me, like terraces, a shoreline, perhaps, an ancient shoreline. So very intriguing. And another one. And this is a great flyover using those same HiRISE photographs. Somewhere there's music. There's the music. We'll spend a couple minutes on this. We got a late start. JD didn't get a start until 5 minutes late, so I got an extra 5 minutes, right? Can you see any river features here? Gullies perhaps here? Look at that, yeah. That's kind of cool right there. Look at it there, right there. Okay, so this photograph, this is the other photographs we saw earlier, was false color. This is actually, if you're actually in orbit around Mars, this is what you see. This is actual color right here. So, and where did the water go is the question. So at one time, they thought there was water on Mars. At one time, it may have had a liquid core, metal core, and it's revolves. It goes, this day is a little bit longer than the Earth. I mean, it's not like it takes months to go around. It goes around about 24.7 hours, something like that. So it's not much longer than a day. So it's got that rotation. At one time, it probably had that liquid core. Yes. What gives it the blue color? I think what that is what gives it the red color. We'll talk about that first. Is whenever that water left, and you kind of alluded to it too. This is kind of the Rust Belt planet. So they think that when the water on the surface, ultraviolet light hit it, the hydrogen went up into space, the oxygen basically went with the iron and made rust, iron oxide. And it's a very dusty planet. You've seen the dust storms that cover Mars. And this, my understanding, is the basalt that underlies a lot of that dust. And when the winds blow, this face of Mars kind of changes. And this is just the underlying bedrock, which is really more of a basalt. Okay, so where the water went is at one time it had a dynamo. But guess what? Mars is kind of small. It goes back to the gravity thing. So it was kind of small. It probably cooled off rapidly. So it couldn't maintain its internal heat like we have been able to maintain on this planet. So when that dynamo kind of dried up, so to speak, even though it's got a decent rotation, unless you have those three conditions, if you have that, you have that conductive core which has that dynamo with that liquid, and to get that liquid, you need that heat. It probably lost its magnetosphere, and when it lost its magnetosphere, then it lost the ability to hold on to its atmosphere, and then the water dissipated. Okay, that's the thinking right now in terms of where the water went on Mars. And talk about oxidation here. What's oxidation anyway? Gee, I don't know. My science is a little rusty. So the significance of this cartoon is the rust on Mars, i.e. the oxidation of the iron. This one here, you've got some pins on. This looks like a vulture, right? It's like a big bird. This is MAVEN, which stands for Mars Atmosphere and Volatile Evolution. This basically got to Mars, I want to say September, it could have been December, just last year, last few months last year. And its whole purpose is to find out where the water went, trying to measure what's happening now in terms of any dissipation of the atmosphere of Mars out to space, and trying to figure out historically where that water went on Mars. That's its primary mission. Can you know what that is? He's thinking. He's thinking. Pardon? No, that's Host. That's Host. Oh, it's Jupiter. Yeah. Oh, okay, I'm sorry, I didn't hear you. Jupiter. So this is a cool picture. Jupiter. Yeah, that's right. Jupiter is about 88,000 miles in diameter, and our moon's about 2,000. So it's like 44 times the diameter of the moon. If you put Jupiter, the moon, out there 240,000 miles away, and you're riding down the road watching the full moon, this is what you're going to see. It is going to be 22 degrees. It's going to be a quarter of the way up the sky. You're going to see this huge figure, and then figure you had too much to drink the night before, I guess. I mean, that'd be kind of cool if we were that close to a planet, right? If we were only a moon of Jupiter, that's what we'd see in our sky. So why do we know Jupiter has an intrinsic magnetic field? Means it's got an internal. It is magnetic. Why do we know that? Pardon? Well, the easy answer is we've sent satellites there. We measured it. You're right. We've actually sent Galileo. Okay, but the interesting thing is, without that, we could have known, if we probably already did know, because it has aurora. All the gas giants have aurora. Both, all four of those gas giants. If you got an atmosphere and you have a magnetic field, you're going to have aurora. Okay, so that's one reason we would know even without having sent spacecraft. And the strength of that magnetic field on Jupiter is incredibly 20,000 times the magnetic field on the Earth. So that's pretty significant. Now, we sent a probe to Jupiter in 1995. It stayed there until 2003. We all know the name of that probe. We do? He was a famous astronomer. He got in trouble. Galileo. So here is the Galileo spacecraft. What are you laughing at? Oh, wait a minute. That's not the Galileo spacecraft. Oh, that's Star Trek. Oh, well, I didn't put that in there. Wait a minute. Here's the real Galileo. Oh, it was J.D. He got a hold of my charts. He always does that. He got a hold of my charts. He put his picture. Alfred Hitchcock always has to have a cameo appearance in his movies. J.D. always has to have a cameo appearance in my charts. I hear rumbling. This is a picture of an artist's conception of this very heavy atmosphere around Jupiter. You go down far enough not to be able to see anything here, but they hypothesize, they theorize that there is a liquid ocean of hydrogen. Deeper still, it becomes so dense and so thick, it becomes metallic liquid hydrogen, and that's the basis of the magnetic field. That very powerful magnetic field. So we all know these. These are the moons. These are the Galilean moons. They're called Galilean because Galileo first saw them with his little telescope back in the early 1600s. Io, Europa, we'll talk about these more at length. This is the big one. This is Ganymede, and we know this in here, Callisto. Interesting thing about this is this is the one that has its own internal or intrinsic magnetic field. These two here, now these have iron cores, so they have that aspect, and this one is mainly ice and rock, but these two also have intrinsic magnetospheres, which means because they're within that magnetosphere of Jupiter, there is some magnetic effect because you can be having it. Venus is the same way. Venus has a, not intrinsic, but I mean induced, has an induced magnetic field, induced by the sun. These magnetic fields are induced by Jupiter. And because they have induced magnetic fields, the only way they could have an induced magnetic field is if there's some liquid inside, and we all know that pure water doesn't conduct electricity, but you have to have impurities, salts and things. So they think there's some salty oceans beneath the surface. You don't hear much about Callisto, you hear a lot about Europa, but they think there's some subsurface oceans, salty oceans, because of that induced magnetic field. It's induced by Jupiter. Right, so yeah. They're okay, yeah, and that's interesting because they're right there in the field. Let me see. Let's next one. And again, that's what I just said. Induced magnetic fields, salty ocean? Question mark. So this is Io, and we went by Io in 1979 with Voyager. We said, oh my gosh, there's active volcanoes on Io. As a matter of fact, there's not many craters here, very active. It's a very hot volcanic planet, their planet, moon. So the question then becomes, what powers the volcanoes of Io? Absolutely. It's too small, too far from the sun. It doesn't have proximity. It's too small to have maintained any kind of decent gravity, heat because of its internal formation, or any radioactive decay, isotopic decay. So what happens is this is that is so close to Jupiter. I think it's about the same distance as the Earth is to the moon. So if you're on this planet, you're probably going to see Jupiter as we just saw it. Okay, the same distance, about 240,000 miles. And it goes around in 1.8 days. It goes very rapidly. It doesn't have that eccentricity. The eccentricity of the orbit's not that great, but it's enough when it goes around and it's so close. And the pull, the gravity between this planet and Jupiter is 300 times the gravitational pull between the Earth and the moon. So look at the moon is powerful enough with the sun to cause 60-foot tides in Bay of Fundy. The tides here, that actually moves the surface like 300 feet. So that's so strong and so powerful. In addition, there's a double whammy because it's got Europa, the next one out that goes around the Jupiter in 2 or 3 days, about twice the time, 3.6 days, because they're in a resonance with each other. Every 2 times, Io goes around, Europa goes around once. So that's part of it. It's getting kneaded back and forth. You take a hard rubber ball, you squeeze it, it's going to get warm. So that's what's happening. It's that kneading effect. And here's an example right here. Here you got Jupiter. The crust is going to move at a larger distance here than it is out here because of that drop-off, that exponential drop-off in the force of gravity. Even this little distance is going to be significant enough to basically pull more on this side than this side and constantly keep that kneading. And then the very rapid revolution around Jupiter. And then you have Europa pulling it the other direction. Okay, this is Jupiter from Europa. It's kind of what we saw before in terms of distance. And you know what this yellow stuff is? Pardon? Pardon? Sulfur. Right. Actually, it's sulfur dioxide coming out of the volcano. Rotten egg gas. The same stuff that comes out of our VOG. Basically, we have a lot of sulfur dioxide in our VOG. I don't think we have sulfur dioxide in the cane burn. That's probably something else, right? And this is Europa. This is the other Galilean moon. And the thing about this is you'll notice where are the craters. And what does it indicate when there's no craters on a surface? Recycled. That surface is constantly being recycled. Just like the Earth, we don't find that many on Earth because we recycle through plate tectonics. And Jupiter doesn't have many craters, or has not that many, because it recycles through volcanic activity. Well, Europa, close up of Europa, it looks like there may be craters here. These just could be areas where there was warm area. It looks like almost like the ice has melted. But you can see here this chaotic terrain, and they basically are pretty sure that's ice. And the next one, like we got two of them coming up here. Okay, this is one you can really see it well. And these are actually actual photos they put together with the Galileo. Tell me when you recognize the music. Somebody recognize that? Moonraker, the winner. That's good. She's good, isn't she? A James Bond fan, right? Ah, yes. Who sang the song? You guys ought to get together. Pardon? Yeah, Shirley Bassey's the answer. She sang the song. Okay. Okay, that moon blew up. Here's a great photograph, not a photograph, an artist's conception of a probe on Europa. Anybody see this movie a couple years ago, Europa Report? It didn't really make the theaters. It was kind of an offbeat movie. It was quite good. It was about this. It was done. NASA approved it because it was very realistic. It wasn't it wasn't a spaceship you'd want to be on necessarily. It was too realistic. But it was a pretty good movie if you want to try to get it on Netflix. So Europa has the same subduction process, they think, okay, they theorize, that we have on Earth with plate tectonics. So when we're talking about ice, we got these plates here that are basically being, subducted under other plates and causing a lot of chaotic terrain, and you got a lot of debris on the top. So they think the same thing is happening on Europa. And here someone asked earlier about the probes. NASA is planning to eventually have probes to go to Europa to drill down through the ice. I've seen numbers. They think the ice is between 1 and 20 miles thick. So somewhere, they could be wrong. It could be more than that. But 1 to 20 miles thick, problematic in terms of getting through it, okay? And then once you get through the ice, 1 to 20 miles, the speculation is this ocean is 60 miles deep. So getting through there and having a probe and would be fantastic to find out what's down there. The question is what lies beneath. I mean, the big mystery. What lies beneath? What kind of life might be there, perhaps? The old maps, 1600s, 1700s, the maps had here be dragons on the edge of the maps where they didn't know where there was terrain. Well, I did read recently that they have never really found these maps with dragons, caricatures of dragons are on the maps, but they've never found the terms here be dragons, except they found a globe from 1510. It's in the New York library, and it says here be dragons, a small globe from 1510. So here be dragons. Now, you get really extra credit if you can name that tune. Where's my person back there that knew Moonraker? Any idea? This is really obscure. Okay, I'll tell you. No, it's good though. It's good to guess. This is the theme song for Jurassic Park. The intro, the overture for Jurassic Park, the original Jurassic Park. That's quite kind of obscure. I try to make all the music halfway applicable to science or science fiction. This is a cool picture. I call it Earth Analog because they have looked at this, and here you can see this looks like similar places like in the Arctic where you have ice flows that are basically pulling apart, moving back together, and that you can see where there's rifts here and where this flow looks like it's overridden this flow here. So because of this, chaotic terrain and the fact that there's no craters, that's why they think that there's a subterranean ocean that has a warming effect that's keeping this stuff moving. And the question is, we're saved, we're saved. These visitors to Hawaii. This reminds me of a bumper sticker I saw in Roswell, Arizona, Roswell, New Mexico one time. It said, "I love aliens. They taste like chicken." For some reason, this reminds me of that. Okay, so Europa, and I don't know if I have a chart. I think I do have one more on Europa. Let's see. Okay, Europa, the question is, why does Europa, again, it's not big enough to have its internal heat source, so why is Europa basically have a warm body of water that's warm enough not to be frozen solid? Pardon? It's the same tidal friction that's affecting Io. Yeah. Do you think it's Io or Io? Do you think it's Io? Okay. Well, I didn't, but I've heard Io and Io. Io, Io. I think of Eau Valley. Eau Valley. Anyway, Io. Okay. This is Europa. They think there could be perhaps twice as much water in Europa as we have on Earth, one you saw earlier. And this just gives you kind of a quick schematic of water on Earth, what they think is on Venus, subsurface, what they think is on Mars, Europa, what we just looked at. This one says it's less water, but it's still kind of the same concept. Enceladus, which we're going to go to next, a little, but it's a much smaller planet. And you notice Titan's is kind of a red color because it's not water, it's methane. It's liquid methane. Okay, we all know Saturn, and this is, again, host. Interesting, this is, what's unusual about Saturn's aurora ring right here? It's real obvious, pardon? Well, okay, that's interesting. I have a backup chart in hexagon. And that originally my chart said what's unusual, and I showed that hexagon. But I didn't put it here because I didn't want to be here all night long. But that's a good point. That's really unusual, that hexagon. You're right. But I talk about this ring because it happens, the magnetic field, the magnetic axis of Saturn happens to be like almost identical with its rotational axis. That's unusual because our magnetic field on Earth is off by 11 degrees. And even Mars is off. The inner planets are off by no more than 11 or 12 degrees. Some of the outer planets are more varied. But this is right dead on. So we're going to go to Enceladus quickly. You can see how small it is compared to the Earth's moon. And it's basically a big snowball. And here's a little bit better resolution, which you have these titles. Oops, I didn't want to go quite that fast. Okay, I got to go back to that again. Okay, here's Enceladus compared to the moon and the Earth. Big snowball. Another better shot of those tiger stripes, and then we'll have another one here. Okay, so what was interesting is Cassini went by this. Cassini is the spacecraft that went around. It arrived in 2004 and is supposedly going to be there to 2017, still going around Saturn visiting all its moons. And they were shocked to see this plume coming off the southern part of Enceladus. Here's a better picture of it. All these cryo geysers is what they call them, and they actually flew Cassini through this to taste it, to see what it is. And what do you think it was? Water? A little bit of methane? What do you say? Chicken. It tastes like chicken. Not like Enceladus, it tastes like chicken. Organic molecules, ethane, propane, acetylene. They were most excited, though, by the presence of what? In that water. Pardon? Well, but what did they say? Salt. It was salty. They were really excited about that. Why were they excited? Because that indicates it has a subsurface ocean. Because the idea is it takes a lot of time for a big body of water to slowly dissolve any salts in the surrounding rock. And when you have a salty solution like that, that's supposedly, according to planetary scientists, a giveaway that there's a subsurface ocean. And the interesting thing about all those plumes of water vapor primarily and salt, they end up becoming the E ring. I don't want to go beyond that one. They end up being the E ring. My trigger finger is too quick. That's way far back. Hold on a second. Let me get there quicker. I want you to see the E ring. There it is here. This E ring, Enceladus is right on that part of the orbit. And you can see right here, this ring right here, this is being caused, they're pretty sure, made of particles of frozen water by those cryogeysers coming off Enceladus. And here's those tiger stripes. There's 4 of these, what's called tiger stripes because of the coloration, where these cryogeysers are emanating from. And that's what it would look like if you were on Enceladus and looking at Saturn. This is the next moon we're going to look at real quick of Saturn. It is the big one, Titan. And that little moon nearby, you recognize that one? You wouldn't. It's Epimetheus. Most of us wouldn't even. That's one of those 67 moons, right? And here is Titan compared to the Earth. A little bigger, quite a bit bigger than the moon. Titan's got a lot of publicity. Here's a near IR, a near infrared image of Titan through that haze of that atmosphere. And you can see the sun in IR kind of gliding off these seas of Titan. And here's a quick kind of cool movie. It's about a minute and a half, if that. This is one of those seas. I think the movie's coming up in a... Oop, I guess I went too fast. Let me go back to that movie. You get a flyover of Titan. Doesn't want to go backwards. Okay, so we've only got about 10 more charts, so we're almost through if you're getting tired. I don't want to go any more than 90 minutes. Don't go so fast? Okay. Want me to go slower? Okay. I just don't want to keep you here longer than you want to be here. Right. Okay. That's true. Seriously, if anyone wants to leave getting tired, you can actually go. Okay. This is Kraken, if that's pronounced right. The Kraken. The Kraken. A Kraken is a mythological Scandinavian sea creature, the Kraken. And they're naming these bodies of water after mythological sea creatures. And you can see these are the oceans of, or seas of liquid methane. Most of it appears in the northern hemisphere. And there's about like 3 named seas and about 30 smaller ones that are called lakes. This is actually the color of what the atmosphere probably would be like there. And again, Cassini, 2004, 2013. This is one of the large bodies. And this is the comparing Legia Mare with Lake Superior. It's larger than Lake Superior. And it's about, they've recently measured the depth of this is about 500 feet as best they can tell. Although they're not too, radar, yeah. Although they're not too sure. And recently I read, and this would be Planet Ocean. I kept calling it Planet Earth, but I want to rechange that name to change the name to Planet Ocean. Lake Superior. And this is like 3 times the size of Lake Michigan and 3 times the water content of Lake Michigan. Or liquid, yeah, I say. This one here is released the Kraken. This is Kraken Mare. And recently they have measured, at least in 1 or 2 spots, they've gone down to 500, no, I think 650 feet. So they're not too sure whether it maybe is deeper than that, the radar doesn't reach, or maybe the radar absorbs the methane, absorbs the radar, and that's not an accurate measure. But they think it could be in those few places they've measured as deep as even deeper than 600 feet, which puts it deeper than the Great Lakes. I think Lake Michigan, I'm not sure about Superior, Lake Michigan I think goes to about 500 feet deep. So pretty significant bodies of methane. And remember, methane on Titan is like water on Earth. You know, water on Earth is cool because it exists in 3 different states. It exists in vapor, in clouds. It exists as water when it falls, as liquid. It exists as frozen ice, all within a few degrees range of temperature. Same way here. It exists frozen. It exists in water as liquid in these bodies of water, and it also rains methane. So it kind of replaces water. So and it's possible there could be an exotic methane-based life form on Titan. Maybe it's I keep pronouncing it wrong, a kraken. Kraken, yeah, released a kraken. And here's actually a photograph. Cassini released this probe, Huygens probe, and here's the photograph of it. But this is when they did kind of an enhancement, and you can see some of these flow patterns. And look at this drainage pattern here. That definitely looks like there's liquid that's basically flowing. Of ammonia, cool, sing along. Cool ammonia. A Western alien. That's what that life form would probably be looking for, thirsting for ammonia. This is an artist's conception. Got to have lightning. An artist's conception of what the surface might look like. And I guess on a good day they got a little glimpse of Saturn there. But this is the flowing methane, and kind of a cool picture. Now here's a bonus question. I'm sure you guys know this. This is a famous drawing, a famous painting. You're right. Who was the artist? Chesley Bonestell, the famous space artist. And this, I think, was done in the 1940s. This is probably his iconic drawing, as best I can tell. So I had to throw it in here. I mean, he was a great artist. He gave me the answer before I gave him the question. Yeah, Jeopardy. There you go. We did Jeopardy last year. Remember that? Yeah. Okay. Now Neptune with host in the background. So, what's unique about Neptune's largest moon? Well, first let me tell you about the largest moon. There's 14 moons in Neptune. Triton is the biggest one. T-R-I-T-O-N. Triton's the biggest one. So of all those 14 moons, 99% of the mass of the moons is in Triton. The other ones are just minuscule. This is the biggie. It's the big moon. And the unusual thing is, we talked about Venus having a retrograde rotation. Triton has a retrograde revolution. So most, Neptune's going around the moon. If the sun's out there going around, Neptune's going around the sun this way, and you'd expect its moon to go the same way. Its moon goes the other way. And it has a high incline. I think it's 24 degrees, something on that order. So what does that indicate? It couldn't have formed in place with its protoplasmary or protoplanetary disk. It's a strong indication that we think it's a captured Kuiper belt object because of that reason, because of its rotation and its inclination also. And its composition is very similar to what we understand Pluto's composition is. So it looks like it was a captured Kuiper belt object. And it is you could almost do a whole talk just on Triton. It's a fascinating moon. They have cryo geysers of nitrogen that are basically just like our geysers of water, other geysers of water. This has geysers of frozen nitrogen. So here's a flyby. And again, Voyager, I think it was in '89, went by Neptune, managed to get these photographs. It kind of looks like a grapefruit. You get all this cantaloupe. What did I say what it was like? Pardon? A grapefruit? Cantaloupe's better. Yeah, it's not a grapefruit. Cantaloupe's better. A muskmelon. Not a very long video, but it's kind of cool. August 29th, 1989. So here's a picture of it. You kind of dwell on it. You can really see this terrain. Really kind of an oddball terrain. So we're getting close to the end. This is what was called snowball Earth at one time. I think the Earth went through periods many, many hundreds of millions of years ago where the entire planet froze over. So it's kind of a cool photograph. But give any alternative? Right? So the question is, why do we explore? And, it's kind of innate within, I think, within our DNA. I mean, it's hardwired to us explore. We always want to wonder, what's over that hillside or hilltop, or what's across that horizon? What's on the other side of the moon or the far reaches of the solar system? Here be dragons. We want to check out those dragons. So it really is summed up quite well by this quote here: "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time," which was stated by who? T.S. Eliot, I hear. Who said that? That's it. That's very good. Yes, T.S. Eliot. Great quote. And if you think about it, that's kind of what we do when we explore. We use the Earth for this, mentioned earlier, the basis of our exploration, what we know about the Earth. We go look at these various bodies and magnetospheres that protect them in terms of the atmosphere and whether it's aurora. And you start looking around. We're not the only, the gas giants all have aurora. They all have lightning strikes. There are dust devils, tornadoes, if you will, on Mars. So there's a very commonality in terms of processes throughout the universe. And by understanding these processes, we understand our own Earth better, and not only where we are now, but where we came from historically, what happened on Earth to bring us where we are, and what might happen in the future, whether it's global warming or global freezing. So when you leave tonight, though, I want you to remember this. Goodbye, Mr. Laufer. And if you decide to write about this, both the Star and the National Enquirer are good possibilities. And then this final little video. Pardon? Okay, from which movie? 2001. Okay, pretty, yeah. Holst. Yeah. And Holst didn't do the Earth. I would make a recommendation that this be added to the host planets as the official theme song of the Earth. Good idea, right? I should say, of ocean. We're changing the name of Earth to ocean. Planet Ocean. I think that's probably the best part of 2001, the scene where they're going through space and the music's playing in the background. There you go. Creates its own gravity, right? Turns. Well, they did that in Interstellar, but it was very rapid. Remember that? Yeah. Yeah, whoa. Pan American, which no longer exists. It's about ready to end abruptly. It ended abruptly. So, thank you very much. If you don't have a periodic chart, I brought some more. Okay. Thank you. And any other questions, just come up. We'll talk about any other questions. We can talk about those. Yes, question. Well, I know it is. I think they crashed Clementine. Clementine was a spacecraft. They crashed into the South Pole, and they were looking at what was ejected, and there was quite a bit of water. Yeah. Well, I think they feel just like there's water under Mars. Now that we're thinking that there's water in many more places than we originally thought. Absolutely. You can create our own water, and you got H2O, you got hydrogen for fuel, you got oxygen to breathe. That's true. Yep. So, yep, and you can have power with, yep, and you can use the UV from the sun basically to dissociate the hydrogen and oxygen. Yeah, that'd be a good. Yeah. There's been a number of studies of that. Yeah, absolutely.